All right, here we go. We have here a velocity versus time graph. And in this scenario, I was watching my dog chase after a squirrel. So we are in the front of my house, and I will bring this up closer in just a moment. Here's my house, this is the rock wall, here's the sidewalk, and there is Romelda. And a squirrel goes chasing by. So I'm going to use my graph to talk about how Romy moved. The positive velocities represents her distance moving to the right and going away from my house. Negative velocity is her coming back. So you can see here, the first 3 seconds Romy takes off. After 3 seconds, her velocity is 0 and she stops. And then for the next 6 seconds, she's again running away at different velocities, right? So she's accelerating, maintaining a constant velocity, decelerating, stopping at this 9 seconds, and then coming back home from 9 to 10 seconds, she's back there. So again, here's an image of my house. Romy runs away for 3 seconds, stops, keeps going for another 6 seconds, then turns around and comes back. So here is our scenario. Now our challenge is to find where is Romy after the 10 seconds. So anytime I'm trying to find distance, where somebody is or position, I can do rate times time. So I'm going to start with this part here between the 5 and the 8 seconds because I make myself a nice little rectangle, and we'll go into why we like rectangles in just a second. Distance equals rate times time. And if you just think about this, like let's just not even think about formulas or think about anything else. Romy is going, her velocity is the y coordinate. She's going 2 feet per second from 5 to 8 seconds. So for 3 seconds, Romy is traveling 2 feet per second. So if we were just hanging out in the front yard watching her go for those 3 seconds, and I said, oh wow, she's traveling 2 feet per second for 3 seconds, how far did she make it during that time? Well, I'm gonna do 2 times 3. She went 6 feet in that time. She went 6 feet in those 3 seconds. And this is the idea of calculus. Given a velocity curve, the area under that curve represents your distance traveled. This, my friends, is the opposite of a derivative. We call it accumulation. How much distance did Romy accumulate over that time? How far did she go? Given a rate of change, how much did you accumulate? Area under the curve is the opposite of derivatives. So let's talk about where Romy is in total. If I want to find her distance, where she went total, I can find all of these areas. So I'm going to go ahead and erase this, but we found this distance was 6 feet. Here, if I want to calculate this distance, again, area under the curve. There's my curve. I've got a triangle that's 3 by 3, so that's going to be 9 halves. Here I have a triangle that's 2 by 2, so that area is going to be a 2, 4 times a half. So I've got, she went 9 halves, plus 2, plus 6, plus, here I've got a triangle that's a 2 by 1, so that's another foot that she traveled. And now what's interesting here, this is how far she's moving away from the house. And we said after the 9 seconds, she starts to come back. So let's see after 9 seconds how far she got away. So I've got 2 plus 6 plus 1, so there's my 9 plus 4.5. So she made it 13.5 feet away, but then started to come back. So what's interesting here, I've got another triangle. It's 2 by 1, so this is another 1 foot. But instead of adding that to her distance and she's coming back, I'm going to subtract that 1 foot to say she is now, after the 10 seconds, she is 12.5 feet from home. So let's go back to that visual. Here's my picture of Romy going. So after 9 seconds, she made it 13.5 feet and then came back a foot. So she is 12.5 feet from the house. And I'm using calculus to find that, area under the curve. This is a little bit different. If I said, how many feet did she travel over the 10 seconds? Well, how far did she actually travel? How much running did she do over those 10 seconds after the squirrel? The answer would be 14.5 feet, right? Because I can count that as a positive. Her total distance, she ran actually 14.5 feet, but since one of those feet was back towards the house, she's only 12.5 feet from the house. So good stuff to be thinking about. Opposite of derivative, we did area under the curve, we did accumulation. If I asked you for her acceleration and velocity, their relationship, acceleration is the derivative of velocity. So given a velocity curve, I can find acceleration. I can find the rate of change by doing the slope of the tangent line. So now moving forward, taking derivatives, a derivative of velocity curve is acceleration. So I got my tangent stick. What is Romy's acceleration from 5 to 8 seconds? Well, that's the slope of the tangent line. She's not accelerating there. She's running at a constant speed. Versus when she first takes off, if she goes from 3 feet per second to 0 feet per second, what's the slope of this tangent line? Her acceleration here would be -1 foot per second squared. Versus over here, from 8 to 10 seconds, what's Romy's acceleration? Well, I'm going down 2 over 1, -2 feet per second squared. That is a lot of calculus. Let's wrap it up. The story of calculus. Calculus is 2 problems. Rates of change, like we've been talking about, that's a derivative. It's the slope of the tangent line. Boom. The flip side of that, the other problem is this idea of accumulation. This is known as the antiderivative. So you've kind of seen that algebraically where you've been finding the antiderivative, or you've been given f prime of x and you found f of x. And some of you may have seen this symbol before. It's like a long S. This is an antiderivative. We're not going to go into that a lot. Don't stress about that. I just wanted you to see it. Graphically, that is your area under the curve. So these are your inverses. If you divide by a rate of change, that's accumulation. The opposite of derivative, the inverse of derivative, is an antiderivative. And graphically, what that represents, it's the slope of the tangent line. Rates of change, slope of the tangent line. Graphically, what does accumulation represent? Area under the curve. Hope you like this video. Make sure you subscribe and smash that like button.